Hello, and welcome to a lecture on circular apertures and beyond. My name is Steve Ellingson. First, an overview of this lecture. The primary topic is uniformly excited circular apertures opening into a ground screen. Now, we covered a similar topic pertaining to rectangular apertures, and in that lecture I noted that there weren't too many applications, and the same is true here. But also, as in that lecture, the reason for doing this is that there is relevance to other things that we are interested in. Specifically, what we'll find is that for a large aperture, the result for a circular aperture in a ground screen is about the same as for a circular aperture in free space. Circular apertures in free space are of great interest because they are good models of things like reflector antennas, horns, various kinds of phased arrays. We'll also talk about non-uniformly excited circular apertures and a particular kind of non-uniformity that we refer to as tapering. So we'll talk about tapered circular apertures. This will become the starting point for reflector feed design. We'll note a connection to Fourier transform theory. In other words, what we'll do is we'll note that observations that we make here turn out to be relevant to all aperture shapes and tapers, and that we can anticipate results and push results in certain directions by exploiting our knowledge of how Fourier transforms work. Finally, before we get started, I'd just like to note that all the references to figures that you may see in this lecture are referring to figures in the second edition of Stutzman and Thiel. Now, if you have the third edition and you'd like to look up those figures, that's no problem. Just remember that Chapter 7 in the second edition becomes Chapter 9 in the third edition, and then otherwise the numbering should be similar. Okay, let's get started. Here is the problem that we would like to solve. It's a ground screen in the z=0 plane. Here you see the x and y axes. The radius of the aperture is A, and it's uniformly illuminated. In this case, we model the illumination as being from a plane wave incident from the reverse side. And it's x-hat polarized. We can say that without loss of generality. And since it's uniform, we just say its magnitude and phase are given by a constant value E0. So in this case, we can immediately write down a pretty good approximation for the far field electric field using type 2F equivalents, and here it is. Note that the field is described primarily in terms of these x and y components of the spatial Fourier transform of the aperture fields. You'll also note here that we have an obliquity factor. This relationship between spatial Fourier transforms and obliquity factors in these expressions turns out to be important later. Now, I mentioned already that even though we're doing just the PEC ground screen case, the result will turn out to be quite general, and we'll be able to apply it to the aperture in free space case as well. Okay, so let's start working the problem. First, the y component of the spatial Fourier transform is simple to compute because there is no y component of the electric field. Therefore, the result of that integration is 0. So all the py's are 0. So our expression for the far field simplifies immediately because all the py's are 0. The px's are not 0. So here we are computing that quantity. When we expand the integral out, and we're doing this in cylindrical coordinates, here's the expression we get. So let's just identify some pieces here. This is the aperture field. It, of course, is x-hat polarized, which cancels with this x-hat out here through the dot product. This is the differential surface element, and it becomes d rho prime d phi. So just to make sure, let's just note how that comes about. So here's a picture you should have in mind. This is d rho prime. This distance here is rho prime d phi prime. So the area of this differential surface element is the product of these two things, which is what you see down here. Also, you see we're expanding the phase factor out as shown here. Now, I've skipped a few steps in working that out, but you should be able to do this. The starting point is as follows. Just remember a expression for r hat in Cartesian coordinates goes like this. X hat cosine phi sine theta plus y hat sine phi sine theta plus z hat cosine theta. And then for r prime, that is the point in the aperture as we're integrating around the aperture, you can write like this: x hat rho prime cosine phi prime plus y hat rho prime sine phi prime. And there's no z coordinate because we're integrating over the aperture, which is the z equals 0 plane. So you take the dot product of these two things, you should be able to eventually get this expression appearing in the phase factor. And I can also rearrange the order of integration here. So I have an inner integral over phi, which looks like this, and then an outer integral in terms of rho. So this is the way I would like to attack this problem. Here I've rewritten the expression from the previous slide. You may or may not know that there is such a thing as a zero-order Bessel function. And one of the many ways to specify or to define the zero-order Bessel function is through this relationship. So I'll simply give this to you as a mathematical fact. The zero-order Bessel function as a function of xi is 1 over 2 pi integral from 0 to 2 pi of this phase factor here, which is plus j xi cosine alpha d alpha, and we're integrating over alpha. So here, what we're going to do is let alpha be phi prime minus phi, corresponding to this thing here, and then xi be k rho prime sine theta. And if we make those substitutions, we can replace now the integral here, and it looks like this. So px is 2 pi e naught times this integral, which is integrating over the zero-order Bessel function as shown here. Okay, here I've rewritten the expression from the bottom of the previous slide. Now we'll do this trick one more time. This time, I'll note that there is such a thing as a first-order Bessel function, which is a function of some variable psi. If I multiply that thing by psi, then it is known that you can compute that as the following integral. The integral of xi times that zero-order Bessel function integrated over xi. So here, I'm still going to say xi equals k rho prime sine theta. And now I can rewrite the previous integral, px, as so. E naught, I've got this factor of 2 pi over k squared over sine squared theta, and then this integral that I've pulled out from up here. And now I can exploit this relationship, and I have eliminated the integral by doing that. So now I get these constants times the first order Bessel function, whose argument is Ka sine theta. Okay, so here is the expression for the aperture fields with Px as the thing we just worked out. I substitute Px back in, so now I've got this first order Bessel function, and I've rearranged constants a little bit for convenience. And note that this thing in the brackets here is the polarization vector. So this is a vector which is saying which way the electric field is pointing, and because of that, I'm going to give it the name E hat, which is a function of theta and phi. So if we look at that this way, we realize that the polarization is being described by this thing here. you can readily work out that the E-plane, that is the plane in which the electric field vector lies, is phi equals 0 and pi. You can try it out. Just substitute those values. Another way of saying that is it's the plane corresponding to E hat equals plus or minus theta. Similarly, the H-plane, being the plane in which the H vector lies, is found to be phi equals plus or minus pi over 2, which corresponds to the polarization vector being plus or minus phi hat. Okay, so here I've rewritten the expression from the previous slide. Now I want to work out the E-plane pattern. Now this is a normalized pattern that I'm going to work out. Just remember what that means. That means the maximum value is 1. So to do that, we write down whatever part of the electric field in the E-plane is varying as a function of the pattern coordinates. And then we figure out what the maximum value over that range is. That's what this means. And in order to compute this, I'm going to play a little trick. I'm going to multiply the top and bottom by 1 over Ka. So I've added this Ka here and this Ka here. The reason I've done this is because this is an obscure but known simpler function that has simple properties. And that function is known as the Jinc function, J-I-N-C. It's analogous to sinc. If you remember sinc is sine x over x, for example. Well, jinc is j1x over x. So jinc is to j1 what sinc is to sine. This is, again, a somewhat obscure but not unknown function. You can read up on it here. You may be able to Google around and find other references to it. The reason I mention it is because right away we know that the peak value of the jinc function is 1/2. You could work this out by doing limits or some other method, just plotting it maybe, but it's known that jinc is 1/2, so I can just pull that out right away. So that factor of 1/2 shows up as a factor of 2 down here. So this is an expression for the normalized E-plane pattern. Now the normalized H-plane pattern is in fact approximately the same, but the nature of that approximation is important to note. They're actually different by a factor of cosine theta. And that cosine theta is approximately 1 near the main beam, and it's irrelevant elsewhere because the pattern is otherwise small. What I'm saying here is we expect to see a pattern that looks like this, a main lobe and a bunch of side lobes. And then we have on top of that a cosine function, or multiplying that we have a cosine function. That's the obliquity function. And what we see is that around the main lobe and the first few side lobes, that obliquity function makes very little difference. It's not till we get out here that the obliquity function significantly changes side lobe levels. So this is the basis for the approximation here. If you get too far away from the main lobe and the first few side lobes, then this is not true. Then it's different by factor cosine theta, and you need to take that into account. Okay, here's a volumetric antenna pattern in terms of the direction cosines, u and v. I've talked about those in a previous lecture. So this is what the pattern looks like. This is obviously the main lobe, first side lobe, and so on. So sometimes these pictures are useful in visualizing the pattern. It's not surprising to see that the pattern's radially symmetric, so the side lobes form rings around the main lobe. However, what we'd like to do now is look at one cut through this thing. So for example, we could make a cut through this thing that like this, that goes up and then comes back down the other side, and then plot that pattern. And we get this. So this is a cut through that diagram that we just showed. By the way, this is for 10 lambda diameter uniform circular aperture. So that would be A equals 5 lambda. So it's a normalized field pattern. So the maximum value is 1, or 0 dB. Just to point this out, this first side lobe level is minus 18 dB or so. Not exactly, but approximately minus 18 dB. And then we see it has a certain half-power beam width, which we could measure or define if we wanted to, and we will in a moment. Now, I've already made this argument about theta not too far from 0 region, right? If I am only interested in this region, then the obliquity factor doesn't really matter that much, and I can neglect it. And if I'm neglecting the obliquity factor, then I'm neglecting the only thing that's different between the aperture in the ground plane case and the aperture in the free space case. So what we can say is that this result applies to uniformly excited circular apertures generally, since P, the spatial Fourier transform, changes more quickly than the obliquity function, and all the differences between the ground plane case and the free space case are related to the obliquity function, not to the Fourier transform. Okay, so let me give you some numbers, some common expressions. It turns out, and you can do an analysis to do this, or you can just believe me, that the half-power beam width for a uniformly excited circular aperture is about 1.020 lambda over 2a. This, by the way, has units of radians. The analogous value for a rectangular aperture was 0.886, not about 1. There's a lambda, and then there's an L, right? So this was whatever L was in the plane in which you were measuring the pattern. So it was Lx for one cut and Ly for another cut. For a circular aperture, we only have one dimension, the diameter. And in fact, there it is. There's a diameter. So you see these expressions are very similar. It's lambda over the maximum dimension multiplied by some number. And that number is 0.886 for a rectangular aperture, and it's a 1.020 for a circular aperture. The side lobe level is minus 18 dB. I'll remind you that turned out to be minus 13 dB for a rectangular aperture. Note here that this does not depend on the dimensions of the aperture. In other words, it doesn't matter whether the aperture is 3 wavelengths across or 30 wavelengths across. The side lobe level is minus 18 dB. That first side lobe level will be about the same distance down, regardless of the dimensions. You cannot change the side lobe level by changing the size of the aperture. Changing the size of the aperture changes the half-power beam width, and that's worth noting. And then directivity. We've noted previously that the directivity of an aperture is, to a good approximation, equal to 4 pi over lambda squared times the physical aperture. So for circular aperture, this is 4 pi over lambda squared times the area of a circle, which is pi a squared. And same result we had for a rectangular aperture. An interesting observation about circular apertures, though, is that we can rearrange this expression a little bit into this form. And that form says that the directivity is equal to the circumference divided by the wavelength squared. So that's a convenient thing to know. The directivity of a circular aperture that's uniformly illuminated is circumference divided by wavelength squared. We've seen a few hints of this already, but now let's kind of lay out the whole story in terms of the connection to Fourier transform theory. We already noted that the far field is proportional to the Fourier transform of the aperture field. They're different only by the obliquity factor, and the obliquity factor plays only a small role if the aperture is large, and the role it plays is limited to the far outside lobes. It's therefore not surprising that half-power beam width and directivity are directly related to the aperture dimensions. We've noted now several times that side lobe level is independent of the aperture dimensions, and this is straight out of Fourier transform theory. In other words, you probably learned Fourier transform theory on time domain functions. So there's a pulse function in the time domain. Its spectrum is a sinc function. Looks like this. And that first side lobe is always 13 dB down, regardless of how long that pulse is. But we also know from Fourier transform theory that if you really want to decrease the side lobe levels, you can do it. And the way you do it is you taper or you window the function. So if we apply, for example, a cosine window to this thing, we get that, right? And then we know that we get something which looks kind of like sinc, except the side lobe levels are down further. So maybe this is minus 23 or minus 26 dB down. So the way to reduce side lobe levels is to taper the aperture fields, and different kinds of windows, different kinds of tapers give you different side lobe levels. Of course, the price you pay for doing this is that the half power beam width is increased. So as this side lobe level is going down, also the half power beam width is getting wider and wider. So there's a built-in trade-off here. You can't optimize both. Again, anticipated by Fourier transform theory. Again, you probably learned this in terms of time and frequency functions, but here we're seeing it has to do with aperture fields and far field patterns. Here's a nice table from your book. It explores this idea of tapered circular aperture distributions. In this case, it's talking about parabolic tapers. So just for reference here, this is the dimension or the extent of the circular aperture. N equals 0 is the case we just looked at, the uniform distribution case that looks like this, just straight across. So for n equals 0, there's the half power beam width we just talked about. There's the side lobe level we just talked about. There's a normalized pattern that we just talked about, and it's called uniform. In this scheme, use n to increase the amount of tapering. It's according to a parabolic function, so n equals 1 looks like a parabolic window applied to this thing. It turns out that that widens the half power beam width, as I just promised. It reduces the side lobe level, as I just promised. And then here is the new normalized pattern. And you can do the same thing for n equals 2. N equals 2 is just this thing squared. That is a more aggressive taper, wider half power beam width, lower side lobe levels, and then here is the new normalized pattern. This thing here is taper efficiency. We're going to talk a little bit more about that later in the course, but basically it's talking about how much power you lose by doing this windowing. Here you've got a relatively large amount of power, and as you do this windowing, you throw away some of the available power that you could have applied to that aperture. So that's what this is talking about. We'll come back to that idea later. Same idea, but now for a slightly different kind of taper. In this version of the taper, you don't go to 0 at the edges of the aperture. You go to some non-zero value. So the author calls this parabolic taper on a pedestal, the pedestal being this thing. But what in fact it is a pretty good model for over-illuminated reflectors. Let me explain that. Here is a two-dimensional diagram of a reflector antenna. And you know that the way reflector antennas work is by bouncing waves off the reflector, and they're collimated and they all go in the same direction. Well, we can think of the fields then from a reflector antenna as being a disk in front of the reflector. And we also know that the way this feed works, it doesn't just stop at the edges. It throws some energy beyond the edges. It spills over. So we know that the equivalent currents in this aperture don't go to 0 along here. There's some non-zero value. So this thing is actually representing a realistic reflector which is experiencing some spillover. The spillover represented by the non-zero values here. And in this handy-dandy plot, you can specify different edge illuminations as this value here, and then find out, for example, what effect this has on the half power beam width, what effect this has on the side lobe level, and so on for different kinds of, or different orders of taper. And then you can even do some finer design here. So for example, here's expressions, or here's a scheme rather, for working out how to determine the edge illumination. So if you want a certain half power beam width, you can work out what K is for that half power beam width based on the simple expression we already talked about. Given K, you can then work out the edge illumination, and given the edge illumination, then you can start to specify feeds that will give that edge illumination to you for a specified reflector. So these kinds of findings are very useful for first cut design of reflector antenna problems. Okay, time to summarize. First, this lecture has been primarily about circular apertures and ground planes with uniform excitation. the aperture is large enough, the obliquity factor, that's this factor of cosine theta, or 1 plus cosine theta over 2, does not significantly affect the main lobe and the first few side lobes. So that part of the pattern is determined primarily by the P's and the Q's, that is the spatial Fourier transforms of the aperture fields. And in that sense, the ground plane solution that we worked out in detail is close enough to the free space solution. The difference between them is only in the obliquity factor, and the obliquity factor only matters for the far outside lobes if the aperture is large. The circular aperture in free space case then is the starting point for design of reflectors. And I didn't talk about it, but also can be used as a starting point for design of horns. And then we talked about the Fourier transform relationship, half power beam width versus side lobe level. The trade-off is implemented by tapering the aperture excitation. And this concept is applicable to apertures of all shapes, not just rectangular, not just circular. This concludes this lecture on circular apertures and beyond.